Good morning, everybody. This is Canada. Good morning, maybe good afternoon or good evening somewhere, some other part of the world. I'm sure right now all of you are staying at home, enjoying the summer. We at School Engineering, we thought it's probably a good idea to actually get in touch with everybody since we haven't seen everyone for a little bit long time. So this is the point that we want to have this engineering roundtable. But before we start, I'd like to see a few things about the unceded territory language. We would like to begin by acknowledging that the land on which we gather is the unceded territory of the Syilx Okanagan people at here. Okay. So again, welcome everyone, and my name is Yan Chou, and I am the Associate Director for Undergraduate Study. As you probably know me, my job portfolio is about student academic study, curriculum development, and accreditation. So it's been a while, we haven't talked to everyone, and we wanted to basically keep everyone in touch and update what's going on at School Engineering and what's going to happen in September. Some of you probably realize September will still be online teaching. What does that look like? What the faculty is doing at here to prepare for September. Although last March has a very fast transition to online. So we're trying to do a much better job in September, of course. Okay, so we're gonna brief that a little bit. And each program chair, oh, by the way, the program chair used to be called program coordinators. So now their title has changed to program chairs. Our program chairs will also brief everyone about the latest news in their program. The news including hiring, maybe including new courses, new curriculum, new research activities. So, and we also see, you can also see, we also have our advising office staff members at here. They are always the best people that you can rely on. So they are here also to brief us what type of support you can get, what type of latest news from university side. Okay. So this is the idea of this roundtable. If you have any questions, you can always ask at the using the chat window. Our host Keela and Sam will help with answering all the questions. And the point here is basically this is a very informal session, so don't hesitate to ask any questions. So having said all this, maybe I'll ask people to have a very brief round of introduction of themselves. And I'll start with maybe the names on my window. Julian, you want to say a few things first? Introduce yourself.
Hello, everyone. My name is Julian Chen. I'm an electrical engineering professor and also serving as a program chair now for the electrical engineering program. My research area is in the general area of wireless communications, but recently I also research the application of machine learning and AI technology for various technology applications. Thank you.
Rini, I think everybody knows Rini. Just quickly say a few things about yourself, Rini.
Yeah, good morning, everyone. I'm Renee Lebo, Senior Advisor with the School of Engineering, and our advising team is always here to support you through these decisions, so don't hesitate to reach out to us. Nice to see everyone.
The names keep jumping. Rehan, Dr. Sadiq.
Hello, everyone. Good morning, good afternoon, and good evening. I'm sure, as Dr. Chow said, that I'm not sure which regions and which places you are in. So the purpose of this session is to make sure that we can deliver you all the new information and especially what's happening in the programs. So my name is Rehan Sadiq and I'm an Executive Associate Dean, School of Engineering. I'm here to support all of you. the idea is to make sure that we will go as smooth as possible during these tough times. Thank you very much.
All right, Dr. SEDIAKO.
Hello everyone, my name is DIMITRY and I'm mechanical engineering program chair, and I have been in mechanical engineering for longer than I want to remember, and I will give a quick snapshot of the things we do in mechanical engineering when I will do presentation on our mechanical engineering program. Welcome all.
And Kayla, I want to say a few words.
Hi, I'm Kayla. I'm the undergraduate program assistant. So I'm here to help you guys out, and I'll be in the back running the webinar.
Thank you, Kayla. Patty.
Good morning, everyone. My name is Patty Osterkoff. As part of the advising team, I work on curriculum, accreditation, and transfer students. So if you're transferring, for those transferring in, I look after those transfer courses.
Great. Samantha.
Hi, Samantha Luco, engineering academic advisor. Same as everybody else, I guess. Same as Patty.
Tamara.
Hi, everyone. I'm the same as Samantha and Patty and Renee, an engineering academic advisor, and always here to help all our undergrad students.
Great. Sam.
Thanks. Hi, everybody. I'm the communications manager for the School of Engineering. My name is Sam Charles, and I'm here to help Kayla support the webinar here today, and look after the website and help to promote some of our stories and some of your successes as you enter into these programs.
Sam is our in-house expert in technologies, computers, videos, microphones. Just in case you have any questions on that, you can always ask him. And now let's hear from our program chairs and see what's going on in each program and what are the updates. And so let's start from civil engineering. I see Dr. Dwayne Tennant's already here. Dwayne, you wanted to take it over from here, say a few words?
Sure. Good morning. Yes, my name is Dwayne Tennant. I'm a civil engineering professor and the chair of the civil engineering program at UBC Okanagan. And we have a brief little slide deck related to me and what I do. As the video kind of already alluded to, civil engineers are involved in all sorts of activities associated with planning and designing and constructing our built environment. And increasingly, we are focusing on sort of safe, healthy, and sustainable construction practices. How do I control the slide deck? Kyla, are you?
Yep, it's me. So you can just prompt me when you want me to move on.
Next. So in terms of me, go back, please. I'm a geotechnical engineer, so geotechnical engineering is one of the sub-disciplines of civil engineering. And you can see some of the disciplines listed in this slide. And it's interesting because, although I've circled geotechnical engineering, if I reflect on what I've done over my career, I've certainly been involved in environmental, water resources, and infrastructure management components as well. And so an undergraduate degree in civil engineering, you may choose to sort of specialize or take technical electives in some of these sub-disciplines. But if you become a civil engineer, your career will always take you in unexpected places. And you basically draw upon your broader civil engineering, or in fact, engineering knowledge to be able to work in those different areas. Next, please. This is a schematic. It's a bit old. This is based on the Rio Olympics a few years ago. But geotechnical engineers are often viewed as designing foundations for structures. In this particular case here, we have a lot of piles. We're an earthworm looking up at various things that geotechnical engineers could be involved in. But they get involved in a lot of things beyond foundations. And that's certainly applicable to me. Next, please. So some of the research that I do and some of the stuff that creeps into some of my classes that I teach are associated with geological hazards that can affect our infrastructure. And I make use of drones or UAVs to collect images, sometimes hundreds, maybe even thousands of images over features of interest. And here's a landslide south of Kelowna near Summerland, where we did some work imaging a landslide, and from those images we can build a point cloud and a digital elevation model. Next, please. And we can look at very detailed features of the terrain. That red arrow is pointing to a green on a golf course that's beside this landslide. And the movement of a landslide has been ongoing for nearly 80 years, gradually growing. And when we were there, we could see a small depression in the green on that golf course. And you talk to the golfers and they know about it, because when they're trying to put their ball into the hole, it has to kind of pop over this little couple centimeter high depression. And that's associated with this landslide. It's gradually growing and starting to encompass this golf course. Next. So I spend a lot of time looking at things that can go wrong, that can affect structures. And here's another example. It's a landslide on the shore of Okanagan Lake in a new residential development. And if you look at the image, you can see multiple retaining walls. There are three retaining walls that have been destroyed. And at the very bottom of the slope, this building that was under construction, the end of it's been sheared off by this landslide. Next. So I was called out to this landslide in the evening, and I flew my drone and I took these pictures, and this is an aerial shot. And if you look carefully, you can see some cracks developing in the slope. And somewhere down there is me standing there. And so I shot these around between 4 o'clock and 6 p.m. And I processed the images to create this Orthomosaic as well as a digital model. And through my analysis, I became quite concerned, and I sent some emails off to the people that were involved in the construction there, and I said, nobody should be allowed onto this property, particularly below the landslide, where the landslide eventually occurred. So this was at basically 6 p.m. Next slide. 10 o'clock in the morning the next day, so shortly after my email was received and they vacated the people, this event occurred. So it can show you how we can use these UAVs to model features that are hard to see at ground level because they're fairly large, and you can make assessments and you can protect people's lives. So nobody was hurt because the evacuation order that was issued was listened to, and people had pulled out. Of course, they couldn't pull out some of their equipment, and they lost some of their equipment at the bottom of the landslide. Okay, next. This is kind of showing you a cross-section of before and after that event, the black being before and the red being after. It gives you kind of a sense of the scale and how far the material moved. So we can do all these kind of things with some of the stuff I do with my processing of aerial imagery. Next. I also look at dams, and in the Okanagan we have probably about 300 small earth dams, most of them providing water for irrigation and drinking supplies. And we've had dam failures. In fact, we've had 14 dam failures in the Okanagan over the last 100 years. This particular one in 2010 caused a lot of damage. Next. the dam is tiny. So there's a picture of a colleague standing in the breach of this dam, and the reservoir is sort of in behind him. It's drained out a day before I took this photograph. Next. And downstream of the small, tiny little dam, major destruction. 5 homes completely destroyed, orchards and vineyards covered in mud and debris. And only by pure luck, no one was killed because the event occurred on a midday on a weekend, and people were not sleeping in their homes at the time. So looking at design and the risk associated with things like earth dams is something that I get involved in. Next. So that's me. You can ask and chat any questions that you may wish to about civil engineering. I just wanted to highlight, and I think it was covered already, but we are starting for the first time a option in civil engineering called the Resilient Infrastructure Management option. And it's a designation that will show up on your transcript, and it talks about and gives you some recognition for selecting courses that are aligned with this resilient infrastructure management focus. So as I said, civil engineering has a range of kind of subdisciplines and dealing with infrastructure and the management of the infrastructure, and designing and operating and maintaining infrastructure so that it can handle climate change and so that it can handle aging processes is increasingly important. You know, infrastructure is in a very expensive part of our society, and as it gets older, it needs to be maintained and upgraded. And if we can do things at the very onset in terms of our design to prolong the life and minimize the cost of maintaining that, so much the better for society. So to do the option, there's no extra course requirements. You do have to choose a more restricted list of design electives, and here's essentially the requirements to have that option. So unlike some of the other options in engineering, there's no extra work involved, but what it does do is it narrows the scope of the electives that you can take and receive this option on your transcript. I think that might be all I have in my presentation. I'm not seeing any chats happening about civil engineering. I don't know if any of the attendees would actually want to, or if they can, ask questions live. Is that possible?
You brief the students some potential hirings, the civil that is going on in civil program?
Who's hiring? Well, the jobs are pretty good right now in civil. The biggest reason is probably the current workforce in civil engineering is a little bit elderly. They're kind of old folks out there, so they're all finishing up their careers and retiring. That alone is creating opportunities for jobs. Of course, the other aspect is that our society and our population is continuing to grow, and we're continuing to build things, constantly building stuff. And if we're not building things, we are dealing with aging infrastructure. And we're rehabilitating and trying to maintain that infrastructure. So the construction and the maintenance and rehabilitation of our built environment is requiring civil engineers. So the jobs are there, they're going to be there, they're not going away, and the job prospects are actually pretty good in BC, in Canada, and around the world.
Thank you, Jane. Dr. Julian Chen, here's your program.
Thank you, Dr. Chow. So once again, my name is Julian Chen. I'm the program chair for the electrical engineering program. So I'd like to give you, for the next 10 minutes, I'd like to give you some additional perspective for electrical engineering. I'd like to start with my first slides with a quote from Nikola Tesla. Nikola Tesla I think his name is quite famous right now. He is a Serbian-born American electrical engineer, best known for his invention for alternating current, or AC current, that is used in every household. Now, in recent years, the name Tesla has become a household name because, you know, an American company adopted this name to become the become the Tesla, known for the electrical car company that is based in Palo Alto, California. Now, Tesla had a number of famous quotes, so I picked this one just because it contains the keyword electricity, which is matches with the electrical engineering. Essentially, he's saying that if you spin or turn around your negative emotion to generate positive, useful, positive energy that can benefit our society. Now, Tesla is not the only famous electrical engineers. Next. And here are some familiar names you may know or may not know. For example, Armstrong was the inventor for the FM radio. Marconi was an Italian electrical engineer who invented the long-range radio transmissions. You may have heard about the Bose. He was formerly an electrical engineering professor from MIT who founded the Bose corporations. And Dolby, Ray Dolby, was the founder of the Dolby corporation, which is listed on New York Exchange. Now, the name Shannon, if you take the fourth-year electrical digital communication course, will appear to you. He was the father of the information theory, which is essentially the mathematical basis for modern internet technology. And everybody knows about Alexander Bell, who was best known for his invention of the telephone, although technically he was the first person who filed a patent, not the first person who invented the telephone. So that tells you the importance of the patent. Jack Kirby, you may not know, he was the co-founder of the transistor at the time when he was with Bell Lab. So he was essentially the father of the integrated circuits. Now, I like to list a Canadian here. He is Edward Rogers. He had a passion for radio transmission, and he actually founded the Rogers Communication. Everybody knows about Rogers Communication. Next. Well, you may, next, please. Well, you may say that all these famous guys are already no longer with us, but I just want to mention one self-made electrical engineer with no introduction. Everybody knows who he is. So Elon Musk, strictly speaking, he didn't receive a formal electrical engineering education. So he started as a physics major, but whatever he is doing right now, or in the past how many years, is all related to electrical engineers. Now, besides Tesla, he is also involved with a company called Starlink. So their ambition is try to shoot about 30,000 micro satellites that would be cover the whole Earth. So as of 2019, I believe the Starlink has already launched about 60 satellites. So they have a long way to go. Today is a very interesting day. So I prepared these slides last night. So I choose this particular picture is to make everybody be aware. Today is a historical day in the United States of America because they have SpaceX, which is a company owned by Elon Musk, which is based in Seattle, is launching the American astronauts for the first time in the last 11 years using American rockets on American soil. So I think you can watch this TV events later today. Next. Now, among all the areas So you have already seen this picture from the YouTube video. I just want to mention my background. So I received my electrical engineering education as my first degree from University of Victoria. And then I moved to Queen's University to study the applied mathematics. Then I realized that my passion was really in electrical engineering. So I went back to electrical engineering and finished my PhD eventually at the University of Alberta. So my areas of research is on the soft side of the electrical engineering that deals with signals, network, and communications. Next. So some of my areas of research, past or ongoings, are related to image processing, optical wireless communications, wireless communication theory, indoor locations, as well as the technology that enables the smart city and smart homes. And currently, I'm also writing a grant application to prototype an intelligent robot using the ultraviolet technology to disinfect the COVID-19 virus. Next. Now, briefly, what is a digital communication system? So every communication system, whether you're using at home or using a modem or a cell phone, they all have something, have this kind of a system block diagrams. So you have information source, you try to perform the source encoding, which is also known as the data compressions, and then you pass something called the channel encoder. So the purpose of the source encoder is try to remove the redundancy from your information source, and the channel encoder try to add the controlled redundancy into your digital signal streams. And then you put on something called a carrier, information carrier. So, and then you transmit over the antennas over a noisy channel, and then you perform the reverse operation. Next. Next. Here's an example of the source encoder and decoder. Is essentially an image compression. So many of you are familiar with the PNG format, which is essentially an example of a lossless compression. Or you may have used something called the JPEG image file format, which is essentially a lossy compression. Lossy means that you throw away some information from the image that is not sensitive to your eyes. So you can see that between left and right image, there's virtually no difference to your eyes, although the information contained on the right-hand side image is less than information on the left-hand side. So for your information, I took these pictures from, I don't know if everybody knows about these pictures. It's a UBC Rose Garden on Vancouver campus. Next. Now, the purpose of the channel encoder is try to add the redundancy into your data stream. So for example, if I'm transmitting a very simple digits of 101001, the simplest format of adding the redundancy, I simply repeat each information digit 3 times. So 1 becomes 111 and 0 becomes 000. Now, because channel is noisy, the received bit streams will be corrupted. So I have used red color to denote the position of the error bits. Now, by a very simple majority decoding rules, I can perfectly recover my transmitted original information sequence. Next. Now, I mentioned about Claude Shannon. He was the father of information theory, you know. Now, Shannon had a very famous theorem called the capacity theorem. I can simply explain to you using a very simple illustration with 1 equation. So the greatness of Shannon is that he was able to come up with a quantity he called channel capacity. So you can consider capacity of channel as the size of the pipe of the water flow. So Shannon was able to relate the capacity of the channel to the data rates. It means how fast you can pump the data over the channel. So he says that as long as your data rate is less than the capacity of the channel, even when the channel is noisy, you can essentially achieve the error-free communication. So, this basic theorem of communication dominates of all our communication device in today's technology. Next. You may have heard about the word modem. Now, the modem actually comes from two words. It's called modulation, demodulation. So what is so essentially demodulation is a reverse process of modulations. So what is modulation? If I have a baseband, so baseband signals, the first top pictures could be represents the signals from your voice. Now, if you try to transmit your voice signals without using anything, you will need a giant size antenna, which is not practical. So what they do is that we put on your baseband signals onto a carrier, which is a fast oscillating sinusoidal signals. So we got the signals called modulated signals on the third row. So this is the signals that is going to be efficiently transmitted over your antenna, which has a very, very small size. Next. Now, to finish my talk, I just want to quickly mention that one of my research is optical wireless communications. You can build this technology into two cell phones. So here I show you two BlackBerry cell phones. You can swap the huge gigabits byte of, for example, movies in a fraction of seconds. Next. You can also use the most of the cars today. They use LED for the lights, and in addition to illuminations, you can also use these LED lights to carry and receive information, such as in the car-to-car applications. Next. Now, bandwidth is always a constraint. So in the future smart city and smart home, you can actually have access to a very high speed data communication link using visible light communication. So your LED lights is functioning both as the illumination as well as the data access link. Next. Finally, I just want to mention that to you that as electrical engineers, we use the AI machine learning technologies in our communication related, or in all areas of electrical engineering, and not just communication. You can use that for machines. You can also use the principle of blockchain to design a very secure communication systems. So if you ask me to choose if I had the chance to choose my major again, I think I would choose electrical engineering again. So I will be happy to answer your additional questions during the Q&A sessions. So that completes my presentation.
Thank you, Dr. Cheng. Let's move on to Dr. DIMITRY SEDIAKO.
Hello again, everyone. And my objective today is to communicate the importance of mechanical engineering, which is the oldest field of engineering. Arguably, it was the very first field of engineering that appeared as mankind developed. And arguably, all other fields of engineering branched off of mechanical engineering at various periods of time, which may include civil engineering, manufacturing, electrical, mechatronics, mining and metals, energy. All these either are or used to be fields of mechanical engineering. So I will start with myself because I think it's the easiest way for me to introduce the field of mechanical engineering using my own examples from my career development. And the main point which I want to communicate, that the field of mechanical engineering is very broad. I started my career very many years ago in electrical power generation, designing control systems for steam generating reactor with a power with capacity of 250 megawatt. And now it's what's the field of automatic control. Soon after, I moved to steelmaking engineering, developing steel alloys and manufacturing technologies for very many applications, including, I spent 10 years of my career in China and Taiwan, developing specialty steel metal alloys, and one of these alloys was used in construction of Taipei 101. You may see this image of this structure on one of these pictures presented on this slide. So what is special about this? Taipei is located in Taiwan, as you all know. It's a highly active region in terms of seismic activity. There are about 2,000 earthquakes every year of different magnitudes. Yes, 2,000 every year. There are high winds, typhoons, hurricanes, you name it all. So the building structure is under enormous load all the time. Because of this high seismic activity, the building is continuously swaying back and forth. And still, that is the tallest building in the world. It has been the tallest for many years until it was replaced with another building, which was built in a different country. But it's still the tallest building in the world ever built in highly seismic active region. So here we go. Combination of mechanical engineering and civil engineering. Soon after that, I moved to the area of light metal alloys, aluminum, magnesium, and also nuclear engineering. You see, I covered very many fields of engineering, but doing all those wonderful things, I was always within the domain of mechanical engineering. I have been working in many countries, in several Canadian provinces. And another example which I want to share with you myself and the people I have been fortunate to work with, we looked in the potential which is rested in aluminum and magnesium lightweight alloys, never fully utilized. And we tried to apply this potential in development of most modern, most powerful, most efficient internal combustion engines. And in pursuit of that, I was fortunate to be involved in developing one of the engines, which received the best engine, one of the 10 best engine of the year award in 2014, and it held this award for the next 3 years. So one of those achievements which I am very proud of, along with several others. And again, that is not strictly speaking, or it is strictly speaking mechanical engineering, but it's branched off into materials and into automotive engineering and into controls. As I said, we develop engines, better to say, we develop materials that can be used in the most demanding application in industries, various industries. In transportation, that is automotive and aerospace. It's used in construction industries. And that is an example of our development of the most critical component of any engine. That's fully aluminum engine block, which was designed for one of GM vehicles. And a major concern with this development was extremely high power and extremely high pressure and temperature this engine has to operate in order to develop the required level of efficiency and also being environmentally friendly. So the objective, the eventual objective of our development is to deliver the materials that can sustain this much abuse during engine operation and still deliver the required power with minimal consumption of primary energy and with a minimal pollution. So the objective here is to develop engines that can deliver 54.5 miles per gallon, which is quite ambitious, and we're almost there, believe it or not. Next slide, please. On the left, you see a mass-produced engine, which is currently used in very many vehicles. That is cheap, easy to produce, widely used architecture of the engine, and very many of us driving these kind of engines, but that is not what we want at the end of the day. And the reason for that, this engine cannot be pushed to any higher level of power, to any higher level of pressure and temperature, just because it cannot take it. The architecture is very weak, the materials are very weak, and we have to go with very many cheap tricks to make it work. So that's not the engine all of us want. We are doing a lot of modeling in designing the new materials and the new engines. And one of the objectives of this design is how we produce the engine and what is the resulted stress distribution in this engine blocks. So that would be important. We know how much to deficiencies of existing alloys and try to boost power on these alloys. So on the bottom right, you see one of those alloys that we designed, and we test this alloy at very high temperature and very high pressure with a cycling load, see how much of lifetime we can expect from this material. Next slide, please. We do both destructive non-destructive testing on our engines and nuclear research facilities, nuclear reactors, where we could utilize the penetrating power of neutrons. We use neutron beam that we shine through our components of our engines, and the information that we receive will give us a stress state of the material of this component. Or we can also use non-destructive, which is quick and easy. You see this engine on the right, where we attached a whole bunch of sensors and we cut it up to small bits and pieces and see how much stress got released. So we're using these both approaches, and also this goes in addition to very sophisticated, very advanced finite element modeling that we do in our development. Next slide, please. This slide gives a quick snapshot of our industry partners. This work that we do is heavily supported by very many industries. This includes primary foundries, international foundries, Canadian, American, European, you name it. This includes major aerospace companies that we work with. This includes automotive companies that we work with. And the alloy that we develop and the coating technologies that we were involved with now resulted in production of next generation engine, which is now went into mass production with BMW. It's also used on some Porsche vehicles, some Mercedes, and recently Ford introduced this engine in its Mustang Shelby vehicle. So the group I have, my students, myself, that we have been working with, we're very proud having these things happening in industry, not only in Canadians, in global industry. And that is where our work goes. So to recap, what I have just introduced you includes mining and materials development. This includes control systems. This includes extensive modeling. This includes manufacturing technologies, casting, alloying, thermal treatment, all this. So there are very many areas in mechanical engineering that we have been using in this line of research. Next slide, please. And we have quite a few research programs that work in parallel with what we do, overlapping with our research, and these areas mutually contributing to each other, advancing each other. Some of our professors, some of our research groups are involved in composite material development. This includes a group of Dr. Milani. My group also does composite materials development. You see this structure on the left. It's extensive finite element analysis on vehicles structure and vehicles shell components. Next slide. We are very active in developing new courses or even new subdomains in the family of mechanical engineering. So some of the subdomains may include manufacturing engineering, which now became a kind of fully independent program within the School of Engineering. Another subdomain is mechatronics, which is now an option within mechanical engineering. Several of our courses lead to aerospace engineering, and that is an example of one of those courses where we're using, there is a very extensive use of computational fluid dynamics. Very many of our courses, in fact, use most advanced, most sophisticated software, which includes, in addition to this slide, we may be using finite element analysis, and we have several courses, both on undergrad and grad level for focusing on finite element analysis, computer-aided design. We have several commercial packages that we're using for manufacturing process computation and for thermodynamics first principles computation, where we compute metals and alloys before we actually produce them and see what they can do for us. I want to, okay, next slide, please. Oh, okay, so that's probably the end. Okay, let's go back one slide. So that is one of the courses. You see the course code is ENGR 491. I want to use another example of the courses, how we are gearing towards online teaching in September. And the course which I want to speak about is ENGR 377, which is manufacturing processes course. And it used to be heavily based on lab projects that used to be done in our EME machine shop. Now, we're redesigning this course, and the lab component, the project component of the course, will be heavily used on using commercial software, very advanced, very sophisticated commercial software in designing processes and establishing the major manufacturing parameters for efficient implementation of those processes in industry. The course will be based on mainly on two packages. One is called EcoCast, and the other is called Forge. And again, we'll be calculating, computing various components that we want to manufacture in industrial setting. Hopefully soon enough we will get back to our labs where we can actually test materials, alloys, and various systems. But all this is actively evolving right now, the way we deliver. The course is online, so the students will not lose anything in the way of their learning, but in fact, they will gain additional skills in using the most advanced software in this example. I mentioned about new programs that are spin off of manufacturing engineering. We have several options. We have minors that we have introduced, including biomedical engineering. And we can speak more about this, but it's probably better if this is communicated by our engineering advisors. Or if you have specific questions about those, don't hesitate to contact me. And I stop here. Thank you.
Well, we have a second. We have a couple of questions that came in through the Q&A section. Abdul was curious about research opportunities available for undergrads, specifically in electrical, but I'm sure you, all the program chairs, can respond to that one.
I'll answer the question a little bit, and then the program chair can answer the second question.
Okay.
Research opportunities, we typically encourage students to approach professors independently. A lot of students start actually approaching the professors starting from their first year. There are funded positions, and there are also volunteer type of positions. Funded positions including the INSERV USRA, UBC, there's a MyTech, there's a work study. So those are funded positions. Some students start their position with the volunteer type of opportunity and then transition into a funded position. And you don't have to stay with one research lab, and you can always transition from one to another one, depending on your interest. You know, some students finally actually enabled to finalize and say, okay, this is my direction, this is what I like, right? So that's actually helpful when you're experiencing different type of research labs, research projects. So the bottom line is a lot of professors are open to getting undergraduate students to the labs. Don't be shy to contact them, and you never know what you end up with.
Just add something, Yang. This is Rehan today. We have also some opportunities which varies year to year related to co-op research positions. So sometimes, you know, especially I feel that in COVID situation, there might be some programs from the Dean's office to create some research internships for the students to do their co-op terms to meet their requirement for the co-op. So this program is not overall the research internship is not a structured program. So there are many things within these research internships. Could be, as Dr. Chow just mentioned, there could be work study, could be maybe directly working with some professor in their labs, do a co-op. So your best bet is directly to reaching out to the professors.
Dr. Chen and Dr. Tennant, there's, sorry, actually, civil, yes, sorry, there's actually civil mechanical. So Dr. SEDIAKO and Dr. Tennant, there's a question about which discipline should I decide between civil and mechanical? What skills are required? Can you guys jump in and answer this question?
You know, from my perspective, I think the skills are the same. They're engineering skills, the ability to learn, the ability to communicate. And I will answer that question by looking at myself. I don't have a civil engineering degree. I have a geological engineering degree. And I taught for 10 years as a mining engineering professor. So I've done geological engineering, I've done mining engineering, and now I'm doing civil engineering. And to make the transitions between those disciplines, engineering disciplines, was easy because first and foremost, I'm an engineer. And so I recall when I was an undergrad trying to decide what discipline to go into and agonizing over the choices. And since then, I've learned it's not super important because your career will take you where the opportunities and your passions lie, and you have the flexibility with a strong engineering undergraduate education to move between disciplines. So you don't have to lose a lot of sleep over your choice. Are there differences? Certainly, and I could try to convince a student to take civil engineering because I'm a civil engineering professor. I'd rather have the student convince themselves about what elements of each of these disciplines sort of speak to their own personal interests and likes, with also understanding that there's really no wrong decision. You'll be successful no matter which specialization you take. Sorry, so it's my non-answer to the question.
I may probably add a few lines to this. What have just been said is absolutely correct. Most importantly, when you become an engineer, you are an engineer. An engineer is a very broad field. So don't be scared to choose something which is wrong for you. There is nothing that is wrong for you. You will always be learning, and both fields are very wide fields. You are acquiring tons of knowledge in both fields, and you can easily, relatively easily, move from one field to another field, but it also means that you have to do a little bit of self-education, acquiring additional skills that you need for this particular workspace or workplace. So you'll be continuously learning, and engineering field is a lifetime learning. There is no way around it. So don't be scared to make a wrong choice here. There is no wrong choice. And I also agree, we should not be convincing you to choose this field over that field. That's absolutely not what we want to do. You have to make a choice for yourself, but keep this in mind. You will always be learning. And if you want to switch to a different field, maybe not, which is not now on your list, maybe you want to go to electrical engineering, yes, you can do it later in your career development.
Yes, that's a tough decision, right? Yeah. A lot of us honestly changes areas over your career. You know, I graduated from a bachelor degree of electrical engineering, but I got my master and PhD from mechanical engineering. So I am part of a mechanical group right now, but sometimes I still think of myself as electrical engineer. So, you know, it's a good match for mechatronics, of course, but that shows you the possibility of a changing career over time. That's a very possible. That actually shows you the importance for our program. We promote this multidisciplinary, the common disciplinary, especially in the first year and in the first term or second year. That helps you to decide, and also helps you in the future to develop this type of multidisciplinary sense. And there's another question on mechatronics and the biomedical option. So I'll give it to the advising office. Maybe Sam or Renee, one of you can answer a little bit about the process.
Yeah, so I believe our office has sent a couple of emails now to students that are eligible for the mechatronics and the biomedical option applications this year, as well as for the RIM options. But essentially the main difference between a minor and an option is that a minor is something totally separate, whereas an option is kind of a focus within that discipline. So as I think Dwayne said about the RIM option, it's sort of like you're kind of specializing within your specialization. So if you are really interested in biomedical engineering applications, but you want to do an electrical or a mechanical degree, you can do that. And then you'll do a normal, say, electrical years 1, 2, and 3, but then when you get to year 4, you'll be doing much more of a focused 4th year instead of kind of choosing electives all over the map when you get there. You can decide at a couple different points to sign up for the options. The option application opens every year for the month of May, basically, and is eligible for biomedical and for mechatronics students. You have to be an electrical or a mechanical student, and you have to be going into 2nd or 3rd year in the following September. So if you meet those criteria, you're eligible to do mechatronics or to do biomedical. And the application is super simple. It's just an online form. You submit your student number and indicate which option you're interested in applying for. Our office will be pulling all those results, and then they'll be reviewed in the month of June, and we'll be notifying all students either way in the month of June so that you know before registration.
The calendar, UBC calendar has detailed descriptive requirements on both options. All options and minors, of course. So those are the places you can take a look at the detailed information. But just to emphasize, the options we have, they are not additional work. There are a couple options you do need a couple additional courses. For example, mechatronics, you need to take a couple computer science course. But you are getting a mechanical or electrical or civil engineering degree, BSc degree, and with the option. So,
Zhang, the next question I think was related to what are the future demands for engineering, and what will be the most or highly demand profession for engineering?
that's a really good question. We have industry and alumni advisory committee meeting almost every year. This is something that we always look into it. You create a program sometimes to satisfy a needs of society, or you create an option. But the way I look at it is, it's like a swing a pendulum. The change of fashion over the years has been from one end to the other end, and then you never know, it will probably come back to the other end. For example, electrical engineering. A few years back, we have relatively low enrollment or interest from students, and but now over the years, and then we start to see and picking up of pace on the interest of electrical engineering, and also there is increasing needs from industry. So it's hard to say what the future will look like, but I think engineering, the good thing is it's a very fundamental needs. It doesn't matter when, you still need metal, you still need electronics, you still need to construct a bridge. So those are the fundamental things that society will continue to need, continue to have a demand. So there won't be a completely wrong or right choice from your end.
Yang, I think one of the questions was whether if you did take an option, whether that forces you to miss key basic subjects and skills. And I think the answer is probably a strong no to that. In fact, your real basic skills and subjects are covered in years 1, 2, and into 3.
Yeah.
Once we get into the options, we're looking at electives, and they are much more diverse in terms of their coverage, and the basic stuff is covered a little bit earlier in the program.
Well, and there are some required courses as well. Like, so if you take, say, the biomedical option and you're a mechanical student, you're still going to be taking capstone, which is a super integral course to the program. You're still going to be taking law and ethics. You're still going to be taking 491 or 492, that's FEM or CFD, which has been identified as being a super important core mechanical skill. You're still going to take 476, which is mechanics of materials 2. It's basically those electives where normally you could choose from a big wide swath of things. You're self-identifying and saying, no, I'm not interested in the big wide swath. I'm super interested in biomedical, and that's where I'd like to focus my electives.
Yeah, one of the graduate attributes required by the Canadian Engineering Accreditation Board is lifelong learning. And I think the whole idea of engineering education is not just for you to learn as many as technical content as possible, but to cultivate a skill of lifelong learning. And then in the future, you can always pick up a new subject on your own, and you can always learn, because there's guaranteed there will be new subjects, there will be new skills that you have to learn on yourself. So the foundations are what we're aiming for, and interests is your 4th year focus, and the future is your lifelong learning skills.
Maybe one small point to add to this discussion. A question was about biomedical option, whether or not student who has selected this option will be missing on the basic mechanical engineering courses or skills. So it has been said, no, you're not going to miss anything. Most fundamental courses that are backbone of mechanical engineering will be delivered from year 1 to year 3, though you have to recognize the fact that some of the options for year 4 will be restricted to biomedical engineering. So you'll have fewer selection if you go for technical electives or design elective courses.
Here, what do we do in management minor?
Yeah.
Okay, that I can maybe answer a little bit. The minor in the management is actually require relatively number of credits than the other minors. I believe it's 24 credits. You need to take first year management 100 course, and the other credits, all fourth year management courses. The original intention for this management minor is to equip our engineering student with leadership skills, management skills, so that they can benefit in their future engineering career. Because you will inevitably not just doing technical work, probably management work. You may end up with leadership in your company. So those courses, which aiming for the fourth year courses, are supposed to give you that type of skills and exposure. So it's not you just doing your regular engineering design projects. So that's the idea for minor in the management.
Yeah, Yang, I will take a little bit more on that. There is a data saying roughly 1/3 of engineers within their first 7 years of their graduation, they start doing some kind of a management job in their job, though their jobs are technical, but they take some management responsibility. So as you know that our engineering curriculum is already one of the longest, I would say, in terms of number of credit hours. So this is not possible to include every single thing in our 4-year or 5-year curriculum. So this is an option available, or minor available for students who are more inclined towards management. They really would like to see them to manage, but still stay in the engineering profession. And also data show that many of our engineering graduates within first 15 years of their career, many of them, I don't know the exact statistics, they end up taking a MBA degree. So what we thought, like even not only management minor, the computer science minor, trying to create more opportunities for our students so they have some kind of an edge, but it requires some extra effort or extra time. So just keep in mind that what exactly your goals are. It's a good idea to spend half a year or a year after your degree and then equip yourself with some additional skills. So that's the idea. And it will be a very basic level management courses. There are, I think, 1 or 2. You will learn basic about finance, maybe a little bit about the leadership, entrepreneurship. That's the overall idea. I think Samantha wants to say something.
I was just going to add, as the main advisor who works with students who are doing the management minor, the main reasons that a lot of students seem to be selecting it is that either they know that sooner or later they're going to be in a position where they will be managing other people, and maybe it's not something they're super comfortable with, or maybe it's something that they want to feel like they're able to do really well. Other students get into it because of they're really interested in entrepreneurship. They want to start their own company, and they know that, if you're starting your own company, eventually you want it to get big enough that you'll have other employees, that you'll have other projects. And some of the 400 level management courses that you would take as part of that management minor are super interesting, depending on your different areas of focus. So we've had students take, say, leadership in complex environments is one of the courses, which totally fits with engineering and the kinds of jobs that you might be doing. There's also courses on specifically entrepreneurship. There's courses on product design, which could be super interesting as well. So it's really something I recommend students read through the course descriptions of those 400 level management courses and see how many jump up at you. It's definitely not something you have to do. If you read it and it feels like kind of, nothing's really jumping out. But if you read it and you find like tons of courses are just jumping off the page, like, oh, I'd love to take that. That one looks really interesting. That one looks really interesting. Then the minor might be something to consider, because it is only 21 additional credits onto your degree. So some students, if they're already looking at being at like 4.5 years, they may just add that minor on, make it an even 5 years to graduate, or an even 6 years to graduate. And then they have that extra notation on their transcript and those extra skills coming out of school.
We have one more question. We're over the time, but I think we can answer that question.
Yang, before you do that, I just wanted to highlight to the attendees that I gave 2 website links to Engineers Canada. And one of them is a labor market report, because a very common concern from students choosing a discipline is, will there be a job for me at the end of the tunnel? And with a high degree of confidence, there will be a job for you, but for you to look at the facts and figures, if you want to explore the files that are posted at the link that I've put under the, I think it's under chat, the Engineers Canada has a nice labor market report, and it gives you a picture of the discipline across the whole country.
Mm-hmm.
Sorry, Yang, you can answer.
Don't worry. Yeah, those are really good information. Okay, there's one question. What are the advantages of doing mechatronics option? Are the computer science courses prerequisites for the design elective in the 4th year? And I could not find a list of mechatronics specific technical electives list online. Okay. I'll try to answer the question, the first part of the question, advantages of doing the mechatronics option. Mechatronics, based on my own experience, I mean, it's a combination of electrical, mechanical, and computer science. So there's a niche market there. Nowadays, a lot of people associate mechatronics or associate other topics with mechatronics. For example, AIs, machine learning, or deep learning with mechatronics. Those are computer science part, I believe. So it seems that, as I said, you know, there's always a market-driven or interest-driven. Right now, the market seems to dominate this, and the market tells you mechatronics is a fairly hot area. And there's industry needs, manufacturing needs, and there's control engineers, robotics engineers. So those are the advantage to learn mechatronics. Those advantage of, you know, doing this option. Again, I think I mentioned about this. There's whether you choose market-driven or interest-driven. So that's the question you had to answer yourself.
Also, regarding the second part about the elective courses, so the full elective list hasn't been published yet because we don't have a set of mechatronics students coming into 4th year this academic year. That list will be published for the 2021 winter academic year, so it should be published in May of next year. So you'll be able to see all the courses then. For now, though, you can read what the required courses are for the option. I see that Sam Charles has posted some really helpful links there to maybe get a bit of a better feel for what kinds of electives and courses you can expect. And there may even be additional courses added to the academic calendar before you would be in 4th year as a mechatronics student.
And by the way, computer science course is not going to be a prerequisite for our 4th year elective course. So you won't have any problem taking all the courses in the list of mechatronics options. Okay, let's answer the last question. And then if please, still you can type, you can still send the question to us. Last question is, I was wondering, will the extra course required for biomedical option be offered during 4 winter semester, especially for students that are in the co-op program, or maybe even online in the summer? Extra course,
so that would be APSI 193, and I know that course will be offered for sure in summer of 2021. I don't know whether it will be an online course or an in-person course. Given the state of the world right now, I can't promise anything, but you can check back with us, and there's a possibility that we would be offering it as well in the following academic year as well. So that would be 2020 winter. We just don't know which term yet.
Okay. All right. I think we're already 12 minutes over the time. And thank you very much, everybody, for joining us. And thank you, everyone, for all the faculty and the staff members being here to help answer the questions. So summer is long, but also short. And hopefully you can recuperate and stay healthy. Unfortunately, we can't not see you in person in September, but we are eager to actually to meet you online in September.
Yang, there is, I know we are already over time, but there is another burning question on mechatronics option. I think maybe somebody can quickly answer that question before we leave.
Samantha, where did I go?
Sorry, I just sent an email because I thought we were closing, so I just sent a message saying that I can answer that by email if you like. There's a couple different links where students can get information.
Sure.
So I suspect it's just there's another one to look at as well.
Looks like there's a lot of interest on mechatronics for sure. Definitely.
Sounds good. Yeah.
Thank you very much. Yeah.
All right. Thank you, everyone. I believe we will have a video posted somewhere on our website.